in 1984. And then he worked as a postdoc fellow in Harvard University in 85 and 86. He then returned to Taiwan, served as a professor here since then. So he has been, more than 25 years now. Let's see. Okay, he received many prizes and awards, and is now a distinguished chair professor of National Taiwan University. I have the pleasure of working with him in the past 25 years and learned many different things from him. In the beginning, he works in hydrogenic amorphous semiconductor. Okay, then he used this small photo CVD system to do the preservation on semiconductors. Okay, at that time, we don't have as many equipment as we have now. Okay, so in the first 3 years, what he had is a photo CVD system plus PL system. We both chip in to get one system. Okay, and FTIR system. That's all. But he can produce many very high quality paper with only those simple equipment. Okay, and then he works sometimes. He spends some effort working in stretching exponential decay. And nowadays, majorly his work is on concentrated on nano material, nano device, and physical phenomenon associated with these nano devices. Okay, so let's welcome Professor Professor Chen.
Good afternoon, everyone. Thanks to our chairman for the introduction. Before going to my talk, I would like to say a few words. And, as a physicist, compared with other scientists, we have a very good chance to understand the physical property of every kind of material much deeper than others. It is because the physics provide the best principle to describe everything in the nature, including from the cosmology to the elementary particle. So with this kind of advantage, so as a physicist, we can combine many different kind of material together. Through the coupling, we are able to predict the new physical phenomena. And so we are able to have the very good possibility to discover new physics through our deep understanding of the material system. And if we discover new physical phenomena, if this kind of phenomena is very useful to mechanical device and with a very high performance, we can find some application. So according to this guideline, I will share with you some of our recent work. The title of my talk today is Design, Fabrication, Prioritization, and Application of Semiconductor Narrow Composite. Okay, if my time is enough, I would talk about all the topics here. The first topic I would share with you is we combine quantum dots called the zero-dimensional semiconductor with one-dimensional semiconductor together to produce a very high efficiency photodetector with a wide spectrum response range. The second one is we combine semiconductor nanoparticle with nanotip to enhance solar cell efficiency. And then the third one is we integrate with the photonic crystal and the semiconductor nanowire to discover a new physical phenomena called the light fountain. I mean, this is a beauty to do the physics. Once you find a new physical phenomena, you are able to give the name, even though this is a small. Okay, maybe this is small, very small, very tiny discovery, but I enjoy it. Okay, and the fourth and fifth part, I will talk about the integration of semiconductor with the liquid crystal device. We discovered several new new phenomena. And the last one, we combine with graphene. That's a very hot topic right now, and we integrate graphene with semiconductor to produce a new light emitting device. Okay, the first one is the integration of the zero and one-dimensional nano semiconductor material. And semiconductor quantum dot has been studied for quite a long time, and it has been known there are many unique features belongs to quantum dot. And the same, similar to the semiconductor nanowire, there are many different kinds of the unusual property for the semiconductor nanowire and also quantum dot. And here you can ask the question: if we integrate this different kind of material to zero-dimensional and one-dimensional material together, what kind of property you can discover? And here I will show you through this kind of integration, we are able to produce we call a perfect nano photo detector. Because this photo detector have an ultra high sensitivity and also have a wide spectrum response. Okay. And in order to have a photoconductivity, the underlying principle to explain the photoconductor is the photoconductivity. It's very simple. If you have an instant light hits on a material and produce electron hole pair, or it is said that if the electron absorb the photon energy and jump to a higher energy state, it has a higher mobility. Therefore, the conductivity through the material is enhanced, and we have an enhanced current. This is called photoconductivity. Okay, that's very simple. Okay, so in this work, we have a very tiny single nanowire that we can fabricate in our lab, and also we have the quantum dot. We can borrow, or we can cooperate with the chemistry or the material science department, or even though the frame in USA to give us the quantum dot, and we integrate, we cut it. This is the, you can see, this is a high resolution image that you can see a spot here. This is the quantum dot, and this large area is semiconductor nanowire. So we integrate together. And the underlying mechanism to have a set after this kind of integration, we have a very ultra high photo sensitivity and also wide spectrum response. The underlying principle is that the first one is the quantum dot has a very high absorption coefficient. And you can say, so you can ask a question, why the quantum dot can have a very high absorption coefficient? I'm not going to explain everything here. So if you want to find this, to have the answer, go back to the fundamental physics, which has been writing in the undergraduate textbook, for example, Holiday. Okay. That's right. Okay. In the Holiday, you can find very easy to find the answer. Okay. Okay. The second one is the probably everyone here has the finished the quantum physics course. If in my class I will ask the student question, why do you think that the quantum dot have a very high adoption coefficient? But here this is not in my class, okay? So that's okay. It's different. Probably again, I can just say 杨信男不在哈，所以我要because he is old enough. If he cannot answer the question, that is okay. Okay. Then the second point is that for a single nanowire, you can provide a very good conducting path. That's very easy to understand. But electron can very easy to pass through along the axis. So you see the main point here is that I have a material which has a very high adsorption coefficient, and one material has provide a very good conducting path. So if I enter these two together, you can imagine that I can have a very ultra high sensitivity combustion material. The main problem right now is after the electron has been excited inside the quantum dot, how can it move into the quantum wire and make the conduction? That's the key point. Okay, so it is not just easy to say the one quantum dot and one nanowire put together. You can have a very good photo detector. No, you have a very have a restriction, and this restriction is a very key factor. You have to choose appropriate band alignment, that's called the TAC2 band alignment between the quantum dot and the nanowire. Because due to this kind of particular band alignment, the excited electron or hole can jump into quantum wire and make the conduction. So that's the key point. And the fourth one is because we know nanostructured material, you have a large surface to volume ratio. Therefore, the coupling strength between the quantum dot and the nanowire can be enhanced due to the nanostructure of the material used. And the last one is the nanowire has a different spectrum response. Quantum dot has a different spectral response of putting together. So we have the spectrum response right now is come from one is from nanowire, the other one is from quantum dot. Therefore, the spectrum response can be greatly enhanced. Okay, that's the underlying principle of our device. So after this kind of design concept, we are going ahead to fabricate the composite material and the device and go ahead to make the measurements. Okay, this is the rate compare the red color curve and the black color curve, where you can see the device with the correlation of quantum dot on top of nanowire. The whole response can be greatly enhanced. Okay, and for the right hand side data, this instant light may have the photon energy less than the nanowire. So in the normal case, if people fabricate a single photoconductor detector from a single nanowire, if the photon energy is less than the band gap, you are not able to produce electron hole pair. Therefore, the photocurrent should be zero. Okay, but here, even though the photon energy is less than the band gap of the nanowire, we are able to see the to detect a photocurrent. That's because the quantum dots right now, he has the spectral response different from that of the nanowire. Therefore, even though the photo energy is less than the band gap of nanowire, we are able still to measure the photocurrent. So these two curves tell us through the integration of the quantum dot and the nanowire, we are able to produce ultra high sensitivity photodetector and with wide spectrum response. Okay, this is our finding. Okay, and this curve to show you much more clearly what I said. After the excitation of the electron from bottom on lower energy state to higher energy state, electron can jump to the nanowire because they have a particular band alignment. So electron here can jump inside to the nanowire and make the conduction. I mean, this is the key point. Okay.
What is SCR?
Which one?
SCR.
SCR is special charge region because they are surface defect here and it can trap charge, so they will produce the electric field in this region. So it's very useful to separate the electron and hole pair. Yeah, okay. So this one end up my first topic. The next one is we integrate semiconductor quantum dots and semiconductor nanotip to enhance the solar cell efficiency. And how can we do that? And if we go back to the working principle of a solar cell, you see usually where solar spectrum is very wide, the wavelength is very wide, not just restricted a very narrow region. So if the UV light comes from the sun, comes from the solar, okay, the wavelength of a UV light is very small, okay. So the penetration depth of a UV light is very close to near the material surface. And however, if the instant light has a longer wavelength, for example, ray color, the penetration depth is much deeper than the UV light. And if the penetration is very close to near the surface, the photo excited electron hole is also very close to the surface, because the surface here has a large amount of defect. The defect can trap a photo-generated electron hole pair, so electron hole have no enough time to travel to the electrode and contribute to the photo voltage or the photo current. However, if the electron, you have a instant light have a longer wavelength and the penetration depth is deeper, you can excite the electron hole pair is inside the back region. The back region have much less defect than the surface. So electron hole pair in this region, after the generation, it can have a very larger possibility to travel to the electrode and contribute the solar cell efficiency. So understand that this kind of the mechanism, the problem right now is to overcome the generation of the electron hole pair near the surface. How do we do it? So if we can design a material system which can absorb the UV light and emit the visible light, therefore we can shift the generation of electron hole pair near the surface to shift that tool into the inside of the back. Therefore, we can enhance the solar cell efficiency. Okay, so that's the underlying principle we think about. Okay, so the problem is how. Is there any material can give us this kind of phenomena? That is the absorb the UV light and emit the visible. So therefore, you see the UV region. UV light is the produce electron hole pair near the surface, and the visible light can produce inside the back region. Can we find such a kind of material system? Yes, we do have it. Okay, this is a zinc sulfide quantum dot. This is the TM image, and this is the absorption spectrum and the emission spectrum. This is the absorption spectrum. You see, this is the UV absorption package near the UV region, and the big emit spectrum is the in the visible region. So this is very different. So we have this kind of system. So if we deposit this kind of semiconductor on top of the solar cell, and I'm not going to go into the detail how to fabricate the solar cell device. Okay. Okay, this is a diagram to show our device structure. We have the fabricated semiconductor nanotip up and down, and on top of that, we deposited the semiconductor quantum dot to see if we can enhance the solar cell efficiency. Okay. And this is our result. The black one is the without quantum dot. The red one is the device with quantum dots. And then you can see the efficiency can be enhanced by more than 10%. Okay, and this is external quantum efficiency, which tells us the instant photon the wavelength. Okay, this is the quantum efficiency, and you can see after the deposition of quantum dots, the efficiency is enhanced. And then we divide these two curves, and then we got a peak position. This peak position is consistent with the absorption peak of the zinc sulfide quantum dot. So this is a clear evidence to show you that the enhancement of the quantum efficiency comes from the absorption of the semiconductor quantum dot. Okay. Of course, we have also done some other measurement to give the additional evidence to show that what we say is true. We have attempted several different kind of quantum dots. One is the lead sulfide, cadmium selenide, and also those quantum dots cannot produce the same effect because they don't have the property similar to the zinc sulfide quantum dot. Okay. So this is here we provide a very easy way to enhance the solar cell of quantum efficiency, and then this we call the frequency down conversion, because we have a particular semiconductor which can absorb UV light and emit visual light. So this is called frequency down conversion. Okay.
Excuse me, so you didn't talk about fabrication. There must be an optimization of kind of the basic.
That's true. So that's the one of the reasons why we use the tip structure, because the contact area between the semiconductor and the quantum dot is much more than the flat one. Okay, if you have up and down, you have a surface area. Your surface area is much more than the flat plain device, right? That's one of the reasons we can see the effect. And for the third part, we'll talk about is the light fountain. I think the people, most of the people sitting here You never hear this kind of name before, light fountain. Probably you hear the water fountain, but you never hear the light fountain, okay? And this phenomena we call is come from the integration of between the photonic crystal and the semiconductor nanowire. Photonic crystal is a very hot topic currently in the every kind of the solid state material, including the metallic particle, semiconductor material, or insulator. Okay, so photonic crystal is very good research area, and of course the semiconductor nanowire. If we integrate these two different materials together, what will happen? Okay, that's a good question to ask. This is what is a photonic crystal? The definition of photonic crystal is very simple. If you have a particle, okay, not necessarily to be nanoparticle, it can be a micro size or even a millimeter size, or maybe bigger. If the size of the diameter of the particle is in the visual range, the people call it photonic crystal. Okay, if the particle size is very large, comparable with the sun wave, the wavelength of sun, then the people call it photonic crystal. Okay, and through this kind of periodic arrangement, it can produce a very unique property, and this unique property is shown here. With their depending on what kind of diameter you have, okay. After the periodical arrangement, you will create a feature you call the photonic band gap, which means that under some certain region, the light cannot pass through the probably inside the photonic crystal. So that's very unusual phenomena. So after this kind of arrangement, we can do the measurement. You can see that this is the transmission, and this is the wavelength. Under certain wavelength, the transmission have a minimum, which means the light under this particular wavelength, the light cannot pass through this material. This is the most important property of photonic crystal, because if you change the instant angle, the minimum position will be changed, because you can see this is if you in normal instant you see the crystal structure in this kind of shape. Okay. However, if you the angle is different, you see the crystal arrangement is very different. Okay. For example, along this direction also, or along this direction, the particle arrangement is different. Therefore, you can see the different spectrum. Okay. Okay, this is a photonic crystal. If you remember, the light is not not easy to get through the photonic crystal due to the periodical arrangement. Okay, after the deposition, we have the photonic crystal, and we deposited the semiconductor nanowire on top of the photonic crystal. We found a very interesting phenomena that we call the light fountain. Right now, the light confined inside photonic crystal right now can be easily get out of photonic crystal, and we detect it. And we use the light fountain this name because we get an idea said usually if the water is buried under the ground, okay. But if you have a pipe dig deeply enough, the water will come out from the tube. Okay, this is called the water fountain. Similarly, because right now light is confined inside the photonic crystal, if we deposit a nanowire on top of photonic crystal right now the light can be easily come through the nanowire. So we call it